Is it working? I do not know. Let's we were here. Twitch. That's me. And if I open Twitch on my phone, then I can see what people say. All the crap that's loud. Advertisement. Ooh, yes, okay. That running. I apologize for the guttural sounds. I am slightly sick right now. I'm going to be sharing some of the links. There we go. Let's share there. I'm going to share this as well on the recent one. Generator. Let's see how that works. And I'm gonna send it to some friends because let's close that. Privacy. Again. Sake. Thermometer. So I'm going to change some coding earlier today. I'm also going to close Slack so you don't see any of my work stuff, which is private. Sorry. And alright, I think I've shown it to everyone that should see it. Ooh, 4 followers. Yes. Anyway. Oh, damn it, I missed the beginning. I wanted to sing the beginning. But yeah, you can tell this is Star Wars. This is A New Hope. That's C-3PO over there. And I was trying to make this be the intro of every one of the episodes with an annoying voice like, "Welcome to Reasonable Coding," or whatever. But we'll see how it goes. Anyways, today I'm going to be working. Let me just close this again. I never know how to exit Telnet. There you go. I'm going to be working some more on Cactus. And, oops, I'm going to also mute my things so it doesn't disturb you either. And Cactus, in case you don't know, is a composable static site generator I've been working on for the past week. And it's a response to every static site generator out there being either slow or just way too opinionated, and me wanting to kill some time while I'm sick. So yeah, essentially what it does is it lets you build a website by throwing a bunch of small site files, which are sort of empty right now, in a Cactus project, and it will go through all of your folder structures however you want to keep them, and it will compile all of your markdown files into HTML, and that's about the only thing it does right now. However, it's very, very fast, and we're making sure, by we I mean Antonio Montero on Discord is helping me out a bunch to make sure that we can continue to parallelize all the work that we can. I guess that from this little tree over here, it's pretty obvious that if you need to compile first post and about me, you can absolutely parallelize those. There's no dependencies between them right now. In the future, there may be some dependencies, such as, oh, the about me has a link to metadata about first post, but right now it doesn't, so it should be okay. And if we figure out how to efficiently parallelize this little graph that describes what has to be done, then As long as we build it correctly, then we should be able to build as fast as we can. So we began this work maybe 2-3 days ago in one pull request that we see here. Effort to fully parallelize the Buildgraph execution, which of course has no description and just a bunch of code. But roughly what it does is it turns everything into promises. If you come from the JavaScript world, you should be familiar with them, or at least have heard of them before. And essentially, instead of executing everything one step after the other, what it does is it will just say, okay, I'll promise you I will compile this file, you go do something else now, and I'll let you know when I'm done. And that means that you can start a lot of processes, not always processes, but computations much faster, and then they will be finishing as fast as they can without you having to wait for all of them to finish in a sequence. Now, we didn't actually need this right now. I'm going to show you a little bit why. The current version of Cactus in a test website, this is a test website. It has documentation folder, let me just clear up this folder a second. Yes. This is a sample website, right? It has a new project folder with a contributing markdown file and some index file describing what it is, and a small side file. It has pages where you would have all of the little posts that you're making. These names can be whatever you want. You could call this Baduba and it will be just fine. Sections is just another set of pages, and inside of sections we have a subsection called Vault that doesn't have a small side file, so it gets ignored completely. And running Cactus right now here, I'm going to run it on the right hand side of the screen here. Cactus build, this is version 0.3 of Cactus. Which, by the way, you should take a look at the manual. It's built with Command Liner, a really nice library for building command line applications. It builds fairly fast. It builds in 6 milliseconds, and sometimes it's even less, like now 3 milliseconds. However, as the amount of files or things that you're building grows up, so if we eventually start doing processing of the markdown files, some templates, or if you want to do something else with them in the middle, like bundling them together or turning them into JSON for your application to consume or whatever, this will start growing in time. We can also see exactly what is going on by calling Cactus build with verbose, and you can add a debug flag to even add more useless information for users, but information is very critical for debugging what the hell is going on. So if we do this right now, you'll see that we start creating a build plan, and it finds a side file at the top level, and it says, oh, there's 2 other files and there's 1 document, and that makes sense. There's a Cactus project and there's a side file, but we also have the one index.md file, which is the doc, right? And then it goes into pages and sections and then Vault, but only actually scans folders that have a site file inside of them. And after that, it says, okay, I've created the build plan. It took 1 millisecond. This is actually very fast, even for really large projects right now. As we'll see in a second. And here we're taking 12 compilation units, which are the different things that we need to build. We need to create a new project folder, a pages folder, a sections folder. So that's 3. We also need to create the output folder, which is the 4th. And then we have 1, 2, 3, 4, 5, 6, 7. So 4 plus 7. Wow. Okay, we have an extra compilation unit here. And I think this is a bug. Look, we found a bug. Cool. Anyways, you can see that it starts creating the folders from the top, and the moment that it creates a folder, it says, oh, now I can compile these markdown files. And then when it creates the next folder, pages, it goes, oh, now I can actually compile the posts inside of pages, and so on until it's done. And that's also fairly fast. Yeah. When we try this in a bigger repository, and I'm gonna just find all the markdown files here. This has 402 markdown files, which might be a lot. But if you clone, I don't know, like 20 or 30 repos for documentation building purposes, then this is not that much, and I would expect it to be even a larger number sometimes, depending on how well documented the replay is. And if we run Cactus build here, verbose debug, then this will take some time. It takes a few seconds. 4.7, not too bad, but it can be made much better. And if you look here, it takes 4 milliseconds to build a whole build plan. After this 4 milliseconds, we know exactly what we need to do and in what order we need to do it. So what we're working with on Monteiro is how can we actually get this to be as parallel as possible. And we had this PR open that had this effort to parallelize things, and the code started to get very complex at some point. A lot of trying to catch some of the Buildgraph execution exceptions and saying things were wrong, but also a lot of, let's say, more heavyweight promise usage. Let me just find a little bit of code that reflects that. Somewhere here, oh, here for example, where we build a waiter promise and then we execute an asynchronous piece of code that eventually, after the target has been compiled and each one of the sub-promises or the dependencies of the target have been folded into a list of promises, then we will sequence them and send them back into the outer promise. And it's very easy, very quickly gets really hard to keep track of. So at some point yesterday, I said, screw it, I'm declaring parallelism bankruptcy and I'm starting over again. And I made a second branch, which is much simpler code, and we're gonna have a look at that. It's called Parallel 2, aptly named. And thank you, GitHub, for letting us take a look at the diffs without actually opening a branch PR. So we're going to be using some asynchronous writing and reading and directory building utilities. We don't need to go in through a lot of details for this, but make.drp will take a path and it will just make sure that path gets built. And write file and read file will write and read files asynchronously as well. Now, the things that have changed from before to now can be seen in this little diffs here. The Buildgraph still has its own sequential execution model, so we can still say, okay, I'm gonna run everything from beginning to end, essentially a depth first traversal of the tree. So you begin with the root, and then you go folder 1, and then you go, okay, I'm gonna run all of the targets inside there, or if there is any subfolder, then I'm gonna go into that folder first, and so on. And then you continue going through the rest of the children. But I've added a separate execute asynchronous function that it's a little bit more straightforward, where once you compile the first target of some build plan, for example, creating the folder that you need to be able to compile the files inside that folder, then you just say, okay, I'm going to get all the dependencies of this first target, and then I'm just going to recurse over the asynchronous execution, so I get promises for each one of them. And once all of them are done, then I'm just going to ignore the results and return out a unit. There's other ways of doing this that are more clean in LWT speech, but this one seemed good enough when I wrote it. Of course, if you're not used to using a lot of operators, you'll be like, what the hell are all the symbols? This one over here says, do the thing on the right after you do the thing on the left. It's essentially an asynchronous semicolon. And this one over here says, once the thing before on the left, which would be this line, right, the line above, is completed, then change the thing, the result of it, with the thing on the right. So yeah, now the parallel execution changed a little bit. So you can see before here we were building, where is it? Right, I think this is the whole function, yes. We were building a list of targets, right? and concatenating all of them after compiling the first target in a given node. So if we call exec, we essentially say, hey, here's an empty list, fill it with targets, and here's a build plan. And then if the build plan is a leaf, we'll just return the empty list accumulator with the target at the beginning. But if it's a node, it means that it's some work that we need to do, and then some subsequent work that we need to do. You could think of this as the dependent, and then, sorry, no. The children depend on the target being done, being compiled. So we need to compile the target first. And once we've compiled the target, we can just collect all of the children in a list. And the reason to do that was that before we were taking a list of all of these children, and we were making buckets out of them. A bucket, if I GitHub lets me do a line here, no, I can't really add comments. But a bucket essentially is a partitioning of a list in sublists of a certain size. I'm going to jump into my terminal now again. Sure. So essentially, if you had a list like this, 1, 2, 3, 4, right? And then you wanted to bucket this in buckets of 1, then you would get 1, 2, 3, and 4, right? I think that's correct. Yes, it would be a list of lists. So if you wanted buckets of 3, then you would get 1, 2, 3, and then you would get 4, and that's it. And I think it failed because of the comments that I'm using. Something like that. So you take a list and you say, give me buckets, so many buckets, and if you tell it to give you 2 buckets, then it will figure out that the size of each bucket should be 2, and then it will do this. But if you say, give me 3 buckets, then it will say, okay, the size should be 1, right? But the last one actually will have a little more, 3, 4. Or the first one will have an extra 1, like 4 there. So that's the implementation details. And then after we had these buckets of work, then we just said, all right, I'm just going to put all those works in different threads of execution, in different sub-processes that will be doing the work. And then when they're done, I'm just going to ignore the results because, whatever. And then let's wait for all of that work to be completed. And that wasn't quite working, but it also led to the more complex approach that we were taking before. Now, that doesn't mean that it naturally had to lead that way. It meant that in my limited understanding of how we needed to do this work, and in the insights that Ann Montero could give me over Discord and the Twitch chat, that's where we ended up. So there might be much better ways of solving the problem that start off from here. I just haven't come across them. Anyways. Now, when we call this execution in parallel, the P stands for parallel, right? The first thing we do is we just compile the first target synchronously, locally, because the first target of the tree will always be the public folder. That means after we go through this step, we know that we have an output directory that it's very safe to write it. And then what we do is we create this little submit function that essentially takes one of the targets, one of the buckets, or one piece of work that we need to do, and it will call the submit function that you have over there, and then it will just log something out immediately afterwards. This is mostly for debugging purposes, so that we know when a task was submitted properly or when it failed to be submitted. And when I say submitted, it's literally one operating system process sending a message to another operating system process saying, hey, here's a task for you to work on. One second. Okay. And I'm back. I will try to mute every time I need to blow my nose or cough. Not to upset anyone's sensibilities, you know what I mean? Anyways, so we wrap the submit function that will send or submit these tasks to processes in this little helper function here. And then we say, all right, given that we know what the parallelizable dependencies are, and this and also first target come from above here, right? Where we take the build plan that you pass in, saying, hey, execute this build plan parallelly, and we say, all right, there will be a first target that always is there. You will always have a first target, and it will extract that target and the parallelizable dependencies. If you're giving it something essentially one compilation unit of work, it will just say, all right, then I'll do that, and the dependencies will be an empty array. So sorry, an empty list. But if you have a graph, right, that has some work and dependent children and so on, then it will say the target itself should be the first target, the first thing we need to do, because this is the root of the tree. The children are parallelizable. So after you get the root right, then you can work on the children however you feel like. And this right here is a very big assumption that we're making, right? We're making the assumption that we're making the assumption that the build plan has been built so that the children are parallelizable in respect to each other, but they all depend on the target. I think a graph or a tree or a DAG makes perfect sense for this sort of work, but we'll dig a little bit more into why this particular usage of children might be broken in a second. So anyways, we take these dependencies, and now we make buckets out of it, and we make as many buckets as we have jobs, which at first sight could look okay. For those of you who have done more parallel work than I have, you'll quickly realize that what happens when you actually have a lot more jobs than dependencies that you can parallelize, then some buckets will end up being empty. And due to a problem in how we are submitting and consuming this work, so due to a problem in how we parallelize this work, we need to make sure that we have enough work for each one of the workers. Otherwise, those workers will never finish. And I believe this is a bug in the library we're using for parallelizing things, which is nproc, which is a great library, by the way. You should have a look at it. I know that Risa has been doing some work in maintaining it, and just recently, Ann Montero also opened a PR to make it compatible with Dune. Sorry, I was reading some of the source code yesterday to understand what the hell is going on inside of it. So yeah, once we have these buckets, which essentially, if I need to make an example, let's say we go to our test website, we have a tree somewhere right here on the left that will, I'm just going to open Vim to write some stuff in there. So we have the first piece of work will be like create a directory, and this directory will be like public, which is the output, and then we have all of the dependent targets, and each one of these will be, again, another node. I'm going to set the formatting to recent so we get some highlighting. Ta-da. And then this will be create a directory, and this will be public new project, right? So in order to be able to compile the dependencies of this particular node, the one that we have here, right, which the dependencies are leaves, insert compile, and then contributing. In reality, these are full paths, but I'm just going to leave the names here so it's a little cleaner to read. Oops. And then I'm going to duplicate this thing. This is essentially the build graph that's being created for this particular project. post, right? And then it continues on for the rest of the project. So these children over here will be bucketed. So if you have 2 of them, right? And then you say, hey, give me 6 buckets, 6. Then you will just get the 1 bucket with the new project one. I'm just gonna call it new project, and then you'll get another bucket with the pages, and then you'll get 1 more bucket with the sections. Oops, this is wrong. Sorry. Okay, and that's it. And then you were expecting 6 buckets, but you have less buckets than you want, because you have less work to parallelize. And once we define these buckets, we essentially will log something out for debugging purposes. Hey, I'm going to submit this many children targets to this many workers in this many buckets. And this will prove very useful for debugging, because the bucketing procedure, the bucketing function was just wrong at the beginning, it had a bug. And then when I fixed that and I changed the implementation, I realized that, oh, sometimes I'm bucketing in more buckets than workers, sometimes less buckets than workers. How can we make this an invariant? So there is always the same amount of workers as there are buckets. And when I fixed the routine, then I realized that sometimes there just aren't enough children to fill in all the buckets. And that's another problem that we have. But essentially, after you have all the buckets, you can just tell LWT, hey, can you please run this submit function in each one of the buckets that we have here? And this means that, and I'm going to switch back to Vim, that if you have, I wish there was a nicer way of drawing things here. If you have the 2 workers, like worker 1 and 2, right? And then you have, sorry, let's do 4 as an example. 3 workers and 4. And you have 4 buckets because you have 4 workers, and then you submit each one of these buckets into those workers. Then that means this one will take care of new project, and the second one will take care of the pages, and the third one will take care of sections, right? And then there will be no work for this one to do, and this one will be sad, and it will never end, and your application will crash. I mean, it will hang. It's a form of crashing. Sorry. So that's where I am right now. What I am going to try now out, and this will again be exploratory phase, is to repartition this this tree, this forest really, right, in such a way that whenever you ask it for 4 buckets, it manages to fill 4 buckets. Now that I'm saying it out loud, it sounds stupid. You may just not have enough work. Okay, so let's write this out for a second. If we were to repartition this tree, I wonder if we should take a look at the amount of buckets that we can come up with even before we create the workers. I'll wait for a second. I know that some of you may have inputs on this. No, my phone died. Damn it. Come on, Apple. Alright, this will take a while. So I'm gonna switch into, I guess, Discord. I'm Ontario saying. Yes, I could also check how Doom parallelizes work. If you have a pointer to that, that'd be amazing. Where is Twitch? Do I have Twitch open here? I'm gonna mute. The first thing I'll do when I get there is mute. Yes, mute. Alright, no comments there. Fibers. That looks a lot like React fibers. But I mean, it's just the same one. That's what I meant. And you fork. Yeah, but that's this forking looks a lot like just making a promise, right? All right, so I guess today's problem with Cactus is how do we partition a tree so that no, you know what? Instead of partitioning the tree, we should begin with something simpler that gives us good results. Or okay, possible options. 1, partition the tree more granularly so that we can submit smaller chunks of work to all workers, just leveraging parallelism. That's fully leveraged. Yeah. The other option would be create as many processes as we can make buckets for. Which is the shitty solution. So essentially, if you say jobs equals 4, oh, by the way, in case I missed it, when you call Cactus build, you can say jobs, and you can say, hey, just use the main thread of execution, or use second thread of execution, or try running like 4. And as you can see, that it's still fast, but there's a lot more work to be done to coordinate this parallel work. So this is much better suited for bigger projects. If you actually want to parallelize any of it, then you have to your typical J, like make J4, that sort of thing. Anyways, so create as many processes and we can make buckets 4. So if you say jobs are 4, and we say buckets 4, but this has a list length of 3, then that means we can really only create 3 workers. So create 3 workers. Yeah. And this relies on the assumption that buckets will always return at most. Okay, so that bucket n will always return at most n buckets, right? So this is the hacky one, that if we do it, sure we'll get something that works. And this is the cool one, because if we do it, then that means that when you call jobs 8, and if you have actual 8 cores, then you'll be doing a lot of work. However, I mean, a lot of work in parallel. However, I don't see any. I'm a little curious about whether we can guarantee that we will be able to give each one of the buckets So maybe what we want is a third approach, right? When we partition the tree more granularly, say we do it on every leaf, which means if we had a node that had like, I'm just gonna copy this over here. If we take this node over here, right, then this thing will become this, right? Where each one of these is a completely parallelizable unit of work. They will have to redo the work of their parent, but we can either we make sure that the work is idempotent. Sorry, I'm eating ice cream because my tonsils are just in really bad shape right now. And after this, right, after we have chunked the work in this fashion, then we should be able to create buckets. However, it will be pointless to, in this case, right, try to make 3 buckets, because at most the length of the resulting buckets that we create, so I mean what I'm trying to say is that at most this will have like contributing and then index. There's just no more work to do. So the partitioning of the graph in this fashion will allow us to bucket things more granularly, which then means there's a higher chance that you'll be able to split work across workers. But there's still no guarantee that you will have enough work for all of the workers, which means after doing the bucketing, that's where we want to say, okay, let's do create as many workers as buckets you could make. And because the bucket number comes from the amount of jobs, right? Then we know that this number, bucket count, has a property that it will always be less or equal than the amount of jobs that you want. All right, so that's my thinking. I think it's just you, Antonio, that are watching this stream. Sorry. So if you have any input here, that'd be great. No worries. It's alright. So I'm going to go with hybrid approach where I parallelize the work by bucketing after partitioning the tree and creating as many workers as we can. Yeah, as we need actually, with a cap on the amount of buckets that we've created. All right. Ooh, this is great. First stream that actually has a well-defined problem to solve. The other ones were like, oh, I'm gonna explore stuff. So yeah, if I go through some of the code that I've written in the second branch, oh, cool. If you haven't seen the work that Antonio is doing on Mirage, just go ahead and check it out. If you search Twitter for unikernel and uniparallel, and what's the name? It's HTTP AF, which I always read it as HTTP as fuck, but it stands for Angstrom Faraday, which are two parsing libraries. So this dude called uninhabited type. Uninhabited type. Inhabited type. I think it's this one. Yeah. Spiros Eliopoulos. Sorry for butchering your name. Really, really cool stuff. Yeah, of course. I mean, he's not gonna be called inhabited type. Like first name inhabited, last name type. That would be hilarious, though. All right, so let me go a little bit through the code that I've written here already. I'll make some of this smaller. Hopefully, you can read everything. I'm gonna open the Discord chat on my phone so I don't have to switch around all the time. All right, so what's going on is that we seem to be checking if the amount of jobs is over 0 and if the size of the build graph is over 50. And if it is, then we will try to spin up a worker pool and then do some work there, right? But if it isn't, then we'll just synchronously execute the graph. Now I would like to do this automatically for the user. I'm not entirely sure if it makes sense for them to be able to tweak this, and I don't quite like the complexity of having it here. But for the time being, I think we could comment it out, right? So every run that we run after this, oops, what am I doing? Should be parallel, so we always will be spinning up a worker pool, and we always will have a number of jobs, but we just don't know yet what the number of jobs will be. And we will always be trying to parallelly execute the build graph. So if we can, we will do it, and it will be awesome, and if we can't, then we won't. So this tells me that we will need to do the bucketing over here. So if we begin by saying, all right, I have this graph, and we already have it, right? The graph is created here in line 12. Then we should be able to call Buildgraph, and then bucket, or yeah, partition. I like the word partition better. And we should keep it jobs as the count of things that it should bucket things work in, and this should return us essentially our buckets, right? Now, what this does is that this function over here should do exactly what we defined over here. It should take this 3 and return this. Yes. Yes, indeed. So naturally, it can't do the work if it doesn't know what data to do the work on, so we need to give it the graph as well. So this will be the root, and then the buckets. So we get the root separately from the buckets so that we can execute the root locally and then the bucket separately. And it looks like we know now how, I mean, we can forget about the implementation of partition for now, and we can just assume that there will be some buckets, so we know that the bucket count, right? which is listed length, is the number that we need to be able to tell exactly how many workers should we use in the pool, because we'll be having at most jobs buckets, right? That means that this length will always be lesser than or equal to jobs, which means we should be able to just use this one instead of the job count. So bucket count. Now, of course, if the partition function is completely broken, then we'll end up with a lot more workers, and this will be completely, this will not do what we expect it to do. And from here on, since we already have the buckets, right, then our parallel execution function then doesn't really need to know the amount of jobs anymore. It does need to know how to submit things into the pool, and it doesn't need to get the graph. It just needs to get the root of the graph and the buckets, and it will need the compilation, the synchronous compilation function to work the root out. Okay, so that more or less makes sense. So if we sketch out this partition function now, then we can modify the execute p function a little bit, which will be much simpler now. I'm starting to think that all right, so we won't really need this function. It will be very trivial to build, and the reason is that it will just call compile on root, right? And then for every one of the buckets, it will just do LWT list map parallel submit, and this will give you one promise back, and that promise back is the one that we will be waiting on. Hopefully that makes some sense. Then now it kind of makes sense for this thing, right, to become this Buildgraph execute parallel. So like the main program module doesn't really know about how we partition things or how we do anything inside. It just goes, okay, I guess we're going to be running things in parallel right now, so I'll just give this function the things it needs. So we can begin here, and I'm gonna do this first by taking the little bit of code, right, taking the submit function and this nice login that we had, right, and moving it over here, so that the submit function, sort of what it does is it calls submit, and then immediately afterwards, since this returns a promise, and this will work. Hopefully that makes sense. Now submit takes some work. It submits the work to the pool, and then immediately afterwards attaches this promise so that we know that the task was submitted correctly or not. I will leave it to do for myself here to do log task completed. I could do it right now, but you know what? I'm just gonna do it right now. Let's make this a debug, and we'll just say task completed. In the future, we can actually assign IDs to this tag, so it will be tasks. It will be easier to say, oh, this particular task has finished or not. And this is getting a little bit wonky, so I'll just pipe it in. There you go. A little nicer, not too nice, just a little nicer. Cool. So what else does Buildgraph do? I'm sorry, what else does execute P do? It already takes the first and the tar, which we do outside. It does compile first target, which we do outside. It does submit, which we do outside. It buckets the jobs, which we already have done. All right, it prints out submitting this many children targets to workers in so many buckets. So if we take that out, right, and that's the first thing we do here. Whoa, okay, ignore that indentation. Then we can just do this. Boom. The first thing it would do, it would say, I'm submitting this many children targets, and pardeps, I guess, would be the size of the whole graph. And to this many workers, which will be the bucket count. In this many buckets, which will be the bucket count, which is nice. Since now the amount of workers will be equal to the amount of buckets, and the amount of buckets is always less than the amount of jobs, less or equals to the amount of jobs that you want, then we can we have that assumption to bank on. And that's the last thing execute P was doing, which means now we can take this whole thing and just jam it in there. Boom. Save. So now what we want to do is we want to build a graph, and then we want to say execute synchronously and parallelly. And now we'll need to figure out a few things. We will need to take an amount of jobs, but we no longer need to take a submission, and we will need to take a plan. Oops, sorry. Sometimes I call plan graph, but roughly should be the same. So let's start the auto-compiling machinery. No module called Buildgraph. Which is interesting. Do I have a typo there? All right, this is inside of course. Now, the Buildgraph module doesn't need to reference itself, so I'm going to remove the references to itself. It shouldn't be too many. Great, so now it's saying that there is no partition function, which is expected. So let's create the partition function here, near. And the partition function seems to be taking a partition count and then plan, right? And it seems to be returning some target. I guess we could use the switch here. So still that switch, select root, and then children, and then this would be the target. Oops. Yes, I realized I could have just taken this code from the prior implementation of execute P, children, and then we can just make it return this. This is of course wrong. But just to make the type checking happy first, and then we fix that. No, we need to add a dependency, and Buildgraph.dune doesn't actually have dependencies on nproc. And it doesn't seem to have a compile-async, which makes sense because compile-async is defined outside. Compile-async is something that the compiler knows about, and it's not something that the Buildgraph should know about. This one is not being used, so I'm actually gonna put it here. All right, so we knew that if we look at the signature, oops, I guess because it doesn't compile it, it can't really know the signature. We need to get the compiler, but we also need to get an async compiler. And we're going to call this to compile async. Okay, which means we will be using this compile that I thought we wouldn't. Duh. So if we pass in the jobs, then we can pass compile and compile async, and we can pass the graphing here. And now we should have everything that it needs. So figure out if we had something else on the way. Honestly, I really like working with Dune in the auto watch mode. It is buggy. It sometimes brings some files from the def. Like you remove something and it for some reason still is there. Like a few seconds later. But more often than not, it just gives me very good type information. Like, oh, you're missing this thing. Like, go here, go there, change this, change that. Which is like pair programming with a computer, which never gets tired of telling you when you're wrong. Cool. All right, so we did not have the size, which we could compute again, but why? Let's just pass in the size. And then line 74, this should be log solidity. Line 81. I confuse. Why? So line 81, this seems to believe that buckets, which is list of plans, So we print the debugging, and once that's out, if we need to print it, right. Okay. So because the partitioning returns, we should write the signature here. This will be an int, and then you will take a plan of some a, and then you will return a tuple of one of the a's, and then a list of plans of a. No, I think you already list the plans. I think. Let's go back to, let's take this signature and go back to our test. So we took one of these things, right? Oh, okay, we implemented something slightly different than what we had specified here. So this takes a node in, which means it takes essentially a plan of some type A. And by the way, the build plan is parameterizable, so you can build other things with it. My intention was to build it so that I can use it right now, but because I have some other ideas of how it could be used, especially when it comes to building applications, which I should probably be looking into Jane Street's incremental instead. I just left the actual work that has to be done internally, so Sorry, that's me eating ice cream. As type variable, so you can use whatever type you feel like. And it should return, it takes one of these in, right? And we want it to return the root which is one of the A's, and then a list of plans of A's, which are each one of these. Yeah. Yeah, okay, I buy this. And the reason it doesn't look too good for this particular one is that in reality, we should do it with a structure that looks more like create there. So I'm gonna just make another tab. Oh, fuck that, please. And here the output should be create there, right? Assuming we're calling bucket and we're saying 4, right? Then the output should be the root, which is create here, and then we have a list, and then we should have at most 4 lists. Let's see if we can fill them, right? And so for the first list, I'm going to be adding one of these. I don't know what to call them. There probably is a good name for it. I should check my intro to algorithms and data structures bibliography to see for better names. But let's call it a path. We'll be writing each one of the paths that we need down here. So the first one is going to be this one, right? And then the next one, I'm just going to open up first this lists. The second one is going to be from line 8, the index. Still same folder, but it's the index now. And then yes, I'm also going to add here for completeness sake, for completions. I don't know the right word for that. I'm going to add the sections folder, which we didn't add before, and this will of course have an about and a hire me, and yeah, that's all. So the next one, the next bucket will get one for pages, right? Which will be the first post. And the next one will get the second page, which will be some other post. Now, the one that follows will be about from the sections folder. So we should see the folder being sections, and then this should be about. And the last one will go into this bucket, and that will be hire me. So if we get this right, then that means we can send each one of these lists into each one of the processes, the workers, and then they will take care of do all the work, and all of the work will be done safely in parallel. Because to build about MD, you will try to build this folder, but folder creation is idempotent. You can build can we consider this idempotent? If it's there, it will not build it again. Or it will. I do not know if make_dir-p actually affects the stat of folder. But for all practical purposes, if I do sections vault, which we already have defined in here, as you can see, this should not fail. It should do nothing. So I could run it a billion times, and then output 3 will be the same. So it should be safe. And the important part is that the actual compilation targets that we have here are done only once. I'm wondering if I'm optimizing this too much for the use case that I have at hand, but this will come up later on as a bad idea, if it is a bad idea. In the meantime, we're all learning a lot about LWT and parallel computing and graphs and OCaml and Dune and all the awesome libraries by the community that I'm using to build this tool. Okay, so because it returns a list of plans, right? Then when we call the partition function here, sorry, let me just root myself. When we call the partition function inside of execute p, which is highlighted here, then buckets is a list of plans. Boom, that makes sense. But it shouldn't. It should be a list of lists of plans, which is what we just saw here. We have the buckets, right? And it's a list that has lists inside. So let's change that. We can do it very straightforward by just saying we always return a list of children, so now the signature will be good. Ta-da! I don't know what the okay, some variable count is not being used there. That's okay. And we have a typo. We have something compile, which I think is compile. No, it's in a different file. Compile should be compile async. And now line 28 says that we have something that doesn't quite work. Alright, I'm gonna name this parameter. I don't know what a beeping sound is. It might be my dishwasher. And wait, I don't need to name its parameters. I just need to check out. Why is size a list? No, it's an int. And this is the build param. And this is the compilation to LWT. And this is compilation to unit. And this is the amount of jobs. So this should be a unit. So character 63 says that the size is not quite what's expected. And that makes sense because we're using the size as a list. Why? Why are we doing that? Okay, that makes a little more sense. Now to simplify this, we don't actually need the debugging to be a promise. We can just put it immediately after and outside. There we go. That built. Good. Okay, so now if we run this thing, and I'm gonna okay, just so for never mind, we can do integrity checks later. I'm just gonna run this thing, and I'm gonna run it first with 0 jobs, and then see it blow up, or not do any work at all. And it's doing something. Actually finished running. What the hell? Okay, verbose, debug. Let's make the autocompiler smaller. Interesting. Yeah, well, of course it will work. We're ignoring the count in the partitioning function. Here, we need to fix this. Okay, so I would expect this to eventually finish, but I'm concerned that it doesn't finish at all. We can tell that there is some interleaved execution going on. Let's try it a few times to make sure that it actually works. So if we look for spinning up worker pool, then we can add to this the number of workers, so it'll be a little easier to understand. Okay, we're gonna spin up one worker, so we submit all the targets to one worker. That is misleading. The size will be actually size -1. The root. So I guess we could just say yeah, this is good, this is correct, but it's I will leave a comment. We're not submitting the root of the tree. This the size. This decrease by 1. And there you go. Now I like it better. It's gonna process 407 compilation units. It creates a directory and then it runs the other 406. Good. So far so good. We still have the stable tool that we can use for verifying that the work that's being done is good. But let's do something else. Let's actually take the amount of jobs into account when we call the partition function. Because right now the partition function is returning one partition all the time. And to do this properly, we essentially can, once we get the, okay, I don't quite know exactly what we need to do here yet. I do know that we will take the children and we will do something with the children. However, we need to traverse the tree and collect each one of the paths from any given root down to a leaf in a list. So let's say collect, let's just call this paths, right? And this will take an accumulator, and then it will take some graph symmetry. So if we just happen to have, sorry, let's just switch on the tree. If we just happen to have a leaf with a target, right? As leaf, we will just return the leaf into the accumulator. The ordering of this doesn't really matter, so we can have the list reversed, and it's okay. However, when we have a node, we have the dependencies there, this node, then what do we do then? Then we want the target to be, oh, right, okay. So if we take all of the dependencies, we kind of have to map over them, right? So for each step, we'll build a new node that has only the parent target and just the depth inside. So this will give us, if we had a node A with B, C, D, then this will give us a list of nodes, right? Where you have node A, B, node A, C, and so on. Oops, like that. And this will work if depth is, if the children are leaves already. However, if the I think that we may actually need to call paths on the dependencies to get the list back and then just attach the node afterwards. So if we call paths, then this will eventually give us the leaves, right? And then for each one of the leaves, we will add the target from the level above. So what I'm saying is, if we have a node A that has a B, C, right? But let's actually explode those. So if this is node B with dependency C, and if this is node D with dependency E, then what we really want, let me just close the parentheses, is a list that looks like node A, node B, C, and just so it's more obvious than this, I'll make a one level deeper, and I will rename all the other variables. So C, and then this is D, right? And then node E, and then this is F. Duplicate this thing and then go like let's say F G H I J K. So what we want out of this is essentially node C, D, and then node E, F, and then G, H, I, then J, K, L. So that way, if we pick any of this, then we know exactly all of the parent work that needs to be done to execute L, I, F, or D successfully. And I don't know how this will work out in practice, but as long as the tasks are idempotent or can verify they are done correctly already, they can be memoized somehow, then maybe this will work. Anyway, I hope this is the output of what we get. So if we call paths, right, and we just shove in the children in here, then we should be able to do base.l.buckets into the amount of buckets. Oops, my Vim worked. There you go. And this will be my buckets. And if the type signatures are correct, it should be a list of lists of plants of A. Boom, there we go. Okay, so let's see how this works. If we do build jobs with buckets in 0, then I just want to see what's going to happen. Okay. Oh, sorry. compilation failed. It wasn't as nice as we thought it would be. Line 27. So this will take a list of plan of A, right? And it will take a plan of A and should return, I spotted the type already. I should return a list of lists of plan of A. No, I should return just a list of, yeah. So that this is a list of plans and this is a plan, and then the return of this branch, right? Be a list of plans and the return of this thing is a list of plans. That makes sense. So children, if children is a list of plans, the path will be a different list of plans, and then this will be a list of plans. And what is your problem here? If that's a plan, an expression was expected type line 28, character 25. Oops, that was not what I meant to do. Line 28, and then we go to character 25. List map, and then for each one of the leaves, which is a plan. Then we will build a node. This expression has type, so I guess this is the lambda. This expression has type list of plan of A to list of plan of A. But an expression was expected of type oh god, of course I need to cancel the accumulator. Depth is the list of plans, and paths with the accumulator. Okay, 1 sec, I'm distracted. checking Twitch to see if I've seen any comments. No, no comments. Hello, viewers. I am being distracted. All right, so if depth is a list of plans, right? When we map over it with paths, then we should get a list of plans. Now when we concat, we get a list of plans again, and then we can just map over it to add a node to each one of them. I actually don't really like that we don't need like that. Yeah, so they should format. Should it format? Oh, it's missing that parentheses. There you go. Alright, so now I'm more like following. And line 34 says, so because children is a path, then oh my god, this sounds like a very expensive. Children is a list of plans and paths work on a single plan. Then now you need to concat again. Oi, oi, oi. And there's something called target that I'm not using there. Okay. Everybody on board with this definition of partition? We'll take the root out and then children, and then for each one of the children we'll calculate all the paths, and then we will concatenate all the paths together, and then we will bucket the paths using count, and then we will return the root and the children. Oh yeah, Smokey Baxter is on board. Cool. Cool beans. This hasn't finished, which is very worrying. But let's run again. Let's run with, I'm going to put these flags first so we can change the jobs easily. Let's run with 1. We expect to see essentially 1 partition. So 1 worker doing 406 tasks. Let's go for it. Whoa! Holy crap, that's a lot of directories being created. Did you compile everything? Why? So many directories being created. RIP, yeah. Precisely. Okay, this is doing some work. I am very curious as to why. No, okay, I'm not worried at all. Of course, it's gonna try to create the directories many times. It's gonna try to create them for each one of the children that we have. So maybe we can optimize there, and if we already have a folder, then we just return. But that's interesting. Let's see if this works with 2 workers. We are trying to send, well, this works. Oh my god, there's so many tiers being created. Okay, so 2 workers, then we probably should have 206 tasks per worker. Now let me run again without stopping the execution. 7 seconds, pretty terrible. Now let's do 4. Now notice that this finishes every time, which is great. It's really, really good. Okay, so there's clearly some work to be done here, and of course, the more workers we have, we should be making a crap load of create directory executions. Sorry, calls. But this seems to work, and it's pretty amazing. I love working with this language. If the types are right, then there's a good chance the code will just work. So now let's do something. We know that making the directory synchronously, right, will, wait, are we making it synchronously? No, we call it execute asynchronously. So making the directory asynchronously will actually block until the directory is created, which might be unnecessary because someone else might already have created it and so on. So we could optimize there. So if we go into the rules of the compiler, and compiler is a bad name for this, it's really just the build rules, if you're familiar with Bazel terminology. And we have this make there async over here that takes a path, just extracts the path as a string and calls make there p async. So we could optimize this base library, and this base module is just a little wrapper around some things that I'm using, like reading files or writing files, or making there in this case. Interesting. So this looks like it will try to get stats from this file, right? And if we get anything, then it just returns. But if it doesn't get something, it doesn't get a stat, right? Then it will blow up. And if it does blow up, actually let's remove the public folder entirely. Now let's see if we're doing the right work. We're gonna run the stable version of the tool, right? And we're just gonna run it. And that's okay, 3.7 seconds. And we're gonna do a small checksum I have prepared here. It finds all the files inside of public and does a checksum of all of them, and then does a checksum of all the checksums. So this should be 32B254. Perfect. 32B on the left, 254 on the right. Great, good stuff. So if we remove it again, and we run the development version of the tool, let's say with 4 threads. Actually, let's just no logging whatsoever, and let's use 4 cores. We can tell this is doing something because the file system change watcher from Dune, it just goes crazy. So now that we built something, we have the public there, we can just make the checksum and see if it's the same. And it is, which is great. At least we know that the work that we're doing is exactly the same work. Now we need to make sure to make it fast. And to do that, what? Oh, sorry, I changed something there. To do that, we can execute everything on a single thread. Sorry, I need to unclog my nose. Letting Montero know that there's something that is working. Finishes every time, and it produces good results. It's still slow, though, but I think it's new tree partition. Mute. And I'm back. All right, so we have something that works, that actually executes the loads in parallel, as we can tell by the logs. It does the right work, as we can tell by the checksums that we're making, the integrity checks. So now let's see why the hell this is slow. And to be able to debug this, let's try to run this with 0 jobs, right? So, boom. That makes sense. So when we run this sequentially in a single thread of execution, and we can verify that by verbose debug, you'll see here then, where is it? There's just one worker. Actually, this is running a worker. And the execution. Okay, so what I was trying to say is that we need to figure out how to run the same process in the single thread. So that way we can enable the profiling library landmarks. And if we do that, then we can simply run the program a few times, identify which ones are the hotspots, and work on those. So for starters, let's just take these changes that we have here, and commit them. because this is very dirty branch, you can tell by the log. Like attempt to run event looping worker to bucket targets before sending the worker. I'll just comment with use as many partition graph and use workers so as many workers should be equal to buckets, which is less than or equal to jobs. Should be enough context for me to write something nice later. Push to the branch, great. So we can do a small quick optimization here and say that if you call execute p with 0 jobs, right, then you will get a single partition, and then this should spin up. But it's going to spin up some workers anyway, and the whole point is that everything runs on the same thread. Okay, so we have two things going on here, right? So the first one is orchestrating the pool of workers and submitting work. And the second one is figuring out what work can be submitted where. If we split those things, then perhaps we could run these bits, right? So we can run this little bits over here in a single thread, and we could also okay, hear me out. What I have in my mind in my mind here is that there will be a module called, let's say, buildgraph.parallel, right? That will actually depend on nproc, and that will let you spawn a pool, and then it will give you back a submit function that when you call it, it will do essentially this. It will make sure that the things are executed in different pools. But we can essentially run a different function, a different submit function, and that different submit function will just will not run in a different thread. So what I like here is for execute-p to know that it has to run this many jobs and use this synchronous and these asynchronous compilation functions and have a plan and a size, right? But be able to both run all of these things inside of a single thread or across processes. In a single process, which is the one that runs the main tool, or in multiple processes. And if we manage to get that, then we can say, okay, execute p, actually, you know what? Just run everything in the same place. It'll be chill. Don't worry about it. And then we can enable landmarks and and debug and see, oh crap, actually everything is much faster now, but building the paths, building the buckets takes so long that it's just insane. It looks slower. So we want to be able to call buckets and then map and submit, right? And this bits over here you want to take out. We want to essentially have some form of like a tear down, right? That when you call it, I guess we could just do this. That when you call it with a unit, it just does something. You don't know what it is. You don't really care where it is either. And this doesn't have to be an elegant abstraction. We can just begin by saying Buildgraph and then just say parallel. RE, and then in here we want create, and this will be very similar to this thing, and it will return as a submit function and a tear down function. So worker count, tear down is function that just tries to close the pool that we have created, and once the pool is done, it just sequences with them pool done. So this should return submit and tear down. We don't need direct access to the pool. And so, yeah. And for submitting things, in this case, we're actually just happy saying like T for task. No, let's just pass in an F, and then this F can be changed depending how we want to run it. But the point of this F is that it will be called and it should return a promise. That compiled. Good. I guess. So now when we pass this compile, we'll see the compile sync is no longer here. So just to keep this somewhere, I'm going to put this here. Okay, so that means this takes a submit function that will just return promise, and it takes a tear down function so that we know how to finish everything down at the end. Great. So when we map over the buckets, we just say, hey, submit it. I honestly don't know how you're going to do that. And when you're done working through everything, we're just going to call teardown. We need to call compile directly though here, so we need to have that there. And we have some errors in line 65. Do not know where those are. Okay, single comments. We do that. This should go away. Okay, now so line 69 now. We are not using this thing, and we can. So let's use it. Cool. So if we go at the signature of execute, then it takes an integer, it takes a function from something to a unit, it takes a list of a plan of something and returns a promise, which is good. And it takes a listed B. I guess that's a result of all of the submissions, which is great. You get your result in the teardown if you want. And then it gets the actual plan to work on, and then it gets the size of the plan. Which we calculated before, so we just pass it in not to calculate again. Alright, so when we call parallel, we give it a function from something to a promise, and this returns you yeah, that looks more like it. So our parallel function here, right? Will go in as, what's the name? Will go in when we actually call submit and tear down from Buildgraph to parallel. And I think we need to add it to the graph. Modules, Buildgraph, and parallel. Well, actually, you know what? It's gonna be automatically compiled. I just need to re-export it. Module parallel. Buildgraph parallel, precisely. And then we'll create. And when we create this thing, it takes I was hoping to be able to create the pool outside when we need it, but it looks like the size of the pool will be calculated inside of execute P. That makes sense. So maybe what we really want here is a pool spawn pool function, right? That will give us a submit and a teardown functions when we call it with a worker count, and of course, these two things will just be, I mean, spawn pool sometimes it could give you a submit and a teardown, then work with them in parallel or sequentially, it should be okay. So if we take this thing and we just turn it around, then we can say spawn pool will be parallel compile. And then we pass it. Boom. I am so worried that this compiles. Okay, but we have our compilation functions here. The asynchronous compilation one will be used inside of the parallel compilation one. This is a terrible name, because this is a function that will be called, right, with some work. So the work is submitted into the pool. And I think a better name for this will be Compile-Sync, because it would just compile everything async. So if we just inline the prior definition of Compile-Sync, we can get rid of one annoying semicolon over there. Boom. And this could be a map in parallel, and then that will already give us a promise. So for clarity, we could just say, take this thing out. Let's call this exec. And let's call this compile. All right. So compilation is compilation, but asynchronous compilation essentially builds an asynchronous compiler with a project, and it builds an asynchronous executor with the compiler, and then maps over whatever plan you have. And this sounds like we can do it once instead of all the time. So if we do this here, then this should be compile-async. Boom. So far so good. I don't expect a lot of people to continue to be following. It's been about 2 hours since we started. Wow. But yes, the asynchronous compiler goes into the asynchronous executor, which in turn will just become a function that compiles any list of build plans asynchronously. And we put that inside a spawn pool, so that when you create a pool and submit a task, then the compile-async function gets called with this task, which is really a list of compilation units that need to be compiled asynchronously as well. So there's 2 levels of asynchronicity, right? The first one is submitting things into the processes, and the second one is how the processes actually compute things internally. This is really exciting for me, at least. I don't know, some people might be like, oh, but this is already, you know, why? Because we can, right? Why else would we do something? Well, that's a terrible way of delivering business value. This, of course, is just a side project. If this wasn't necessary, then we wouldn't be doing it. No, didn't like that either. All right, so when we do the execution, the first thing we do is we partition the tree. So now we know how many workers we need, and then we say spawn pool, and this spawn pool will effectively give us a way of submitting tasks into the pool and tearing down the pool. So for each one of the buckets, we will just submit all of the tasks asynchronously, and then once everything is completed, then we will just tear down. And once the tear down is done, we'll finish running the program. Which means running this thing, and again I'm gonna change the order of params. Should take as much as it used to take, and it should produce the same output, which is through 3 to be 254. Good. Okay, so this is still working. I'm surprised that it is, but I'm also happy. So now let's do the following. Now we're gonna change the way in which we execute this, right? Essentially by checking in how many jobs we are passing in. So if we have more than 0 jobs, then we will just spawn at least one worker, and we'll be doing some things in there. However, if we pass in jobs 0, then everything should run in the same thread. Although it would still be asynchronous, right? It will run on the same thread. The interesting bit here now is that even though compile and graph and size would be the same, the spawn process function will be different. So the Buildgraph has a parallel module. Let's make a sequential or just an async module. Buildgraph.async.create, and I am guessing this one will require us to pass this in the sync compiler as well, so we can put that in there. Sync. And if we rob the parallel model, then this is the code that we used to have before. We need to return a submit and tear down functions. But right now I'm just gonna remove all the code that's related to nproc. So if we debug anything, we're not going to be saying spinning up worker pool with some workers. We are we can say reusing event loop from main process. Good. And then submit will take some work, and now this promise doesn't actually have to be this. I think in this case, submit just will be an identity function, and the tear down will just be an return unit. Well, I mean, of course, we need to call f with a submit will just be f. We're not using this thing here. We are not using the worker count at all. So if we just expose async, boom, compiles. Oh, if you really like the camera and return, this is so nice. Right, so if we run this again with 4, we'll see that it does say, hey, creating a pool, if I find that all the way up there. Creating build plan, spinning up worker before pool, 4 workers, right? If I run this with 0, it should not say that. It should instead say reusing event loop. This is too damn fast. Reusing event loop from main process. Nice. Cool. So just out of curiosity, I'm going to run it like 0 there. See how fast it is. Not bad. 1, 2, 4. Okay, still very slow. Let's see what we can do about it. But the good thing is now we have no workers being created whatsoever, which means that debugging everything will be, profiling this thing will be much faster. And we want to profile the Buildgraph module. So if we go into Buildgraph tune, we just need to add a dependency. But before we do that, I'll just do something that I haven't seen around. I think people don't actually like other people doing this, but it makes it much easier for me to understand what dependencies are where, because now I can sort them. And I want to add landmarks, and I want to add landmarks. There you go. I want to add a PPX here, so I'm going to go to landmarks first. Why do I have Axis open? Go away. Where are you, landmarks? There we go. And somewhere in here they have this PPX, but in the example they have they had something slightly different. Simple 2. Right, they had out. Okay, so I'll just take that one. Huh. Oh, right. No. POM landmarks, and let's wait the development time. Development time dependency. I wonder if we need to add something for PPX. Wonder why, wonder why. Okay, so let's trust tune here. It says you should probably run tune external live tabs missing. Oh, okay. But there isn't a package called that. Huh. Interesting. How did I run this before? Landmarks. Do I have a typo in the name? Okay, so there's a typo here, and we can quickly submit this. Propose update example with write ppx package name. It's trying to use this. First mine realized done sample file was using a package that I just couldn't find. This seems to work. Thanks for the library. Propose file change. Cool. So this means that now, landmarks, if we run this thing with a camel landmarks on, then we should get some output. And, well, not quite. Partitioning is not that expensive. If we add it to the compiler itself, we can see the build. Yeah, okay, so partitioning is actually not that bad. Let's send this to Montero. And over here, let's see if Landmarks has a way of showing me how much time was spent on something. I appreciate the cycles, but I'd like to see the actual impact that you had. Okay. So the hotspots here, I mean 35 million cycles. Don't seem that much. But Buildgraph is taking a long time. So let's try to get into the compiler. See if there's some, and I'm already out there. I already am there. The compiler is not actually spending that much time, is it? 18 million for this calls, compile sync, make the sync is 16 million. Okay, so this is not really doing much to dispatcher, which it's okay. But exec takes the cake. No, my bad. It's a Buildgraph P. Buildgraph 2. This spawns a pool, some workers, the compiles root, and debug some crap. I wonder what would happen if I call it 4. It breaks royally. Which makes sense. Hey, it's stream working. I'm here just profiling some code, taking a look at why on earth it's taking this long, and is it something I'm doing that's wrong, or is it really just taking this long because it has to? So the premise is that the single-threaded execution asynchronously should take longer than the, sorry, should be actually faster than the other one, but interesting. Yeah, no. No, okay, well, I don't want to say that I'm giving up on this, but current master running on 4 threads, workers doing the work sequentially, and each one of them is about 2 seconds faster. All right, these have been great experiments in working with LWT. Parallel in sync. And I have enjoyed myself very, very much, learning a lot about LWT, how it works internally, how to do profiling. I hadn't done profiling like this in a long time. The browser tools for JavaScript profiling, which are the ones that I've mostly used, are really, really good. But then again, they have whole teams working with these things. And I guess what I'm saying is that the OCaml community could use some people that like profiling to get more time into libraries like landmarks, which feel very, very nice and robust. And even though they don't support like multi-process process profiling, they even allow you to. I mean, they don't support it automatically via the PPX, which I think is great, by the way, that you can just throw in a PPX and it just booms. It just profiles the whole thing for you. But it does support the multi-process profiling if you're willing to go in and do benchmarking manually, which is also great if you really want to track down what's fast, what's not, what's where. So I guess what I'm saying is that the second attempt of parallelizing has taught me a lot more, but it doesn't seem that parallelizing this workload is going to make things any faster. Is that what I'm saying? Now I kind of want to take a look at the benchmarks for the base module and see if the problem was that the writing and reading of files is much slower or not. It used to be faster, and then the compilation was the bottleneck, which is good. But there are still some bugs when you use many cores, such as 8 or 16, as we showed before in the little snippet that I sent on Montero. Should be over here. When I tried running Cactus, the new dev build with 8 jobs, 8 cores, it just hang. And it's also been 2.5 hours of non-stop working on this, and I need to take a break. Yeah, as Montero says, this is probably enough time to be spent in parallelization, which is good enough. So thanks a lot if you were listening. If you liked any of this, just leave a star, leave a +1 on the Look What I Built channel, follow the Twitch stream or whatever. I'm going to continue to work on this a little later on today. I think the next thing that I'm going to work on is actually do templates for you to be able to put all of your posts inside of the send template so they look kind of similar, which it's impossible right now. I mean, you would have to copy and paste the whole template over and over. And I need to make some decisions there, whether I want to stick with something like handlebars, whether I want to use some literate OCaml or literate reason to be able to embed the contents, the compiled contents of the post into some template that you want. And yeah, I'm gonna be doing that, considering trying to make the least amount of assumptions possible, so you can write the template and do anything that you need to do, or rather than I need to do. I'm building this so I can continue blogging, because I forgot how my blog works. And Rack and Pollen are amazing tools, but I just don't have the time to invest in those right now. I guess it doesn't make sense that I invest in this, but hey, at least I'm learning something cool. Not that Rack and Pollen aren't cool, they are. Anyways, thanks a lot for today. Stay reasonable and go hack on something you like. This has been trying to parallelize Cactus, a composable static site generator. and this is Reasonable Coding. See ya!